let's get started. So yesterday where we left off was right in the middle of doing typed closure conversion, right? So I've put the source and target languages that we were working with yesterday on the board just to get us started again. And I want to clarify a couple of things before I move on. So what we're doing is translating from our source language, simply type Lambda calculus, into this target language where we have existentials. And in particular, we're doing closure conversion, right? So we want to make sure that all of the functions that we produce, the translated functions, we want to make sure that the bodies of all lambdas are closed. They must contain no free variables. So in order to do that, I actually should show you the lambda typing rule in the target language. The target language is designed, yesterday I said that the type system is standard. It is completely standard for the source. But in the target language, there is one thing that is non-standard, which I forgot to mention yesterday. So here it is. Here's our rule for how we type check functions in the target language. So remember, we have these multi-argument functions. Lambda x, take an argument, dot e. So when we type check our functions, we want to make sure that the body contains no free variables other than the ones that appear right here. Okay? So I'm going to say that this function cannot have any free type variables, and the only free term variables that it can use are these x's that were actually passed to the function. Okay? Nothing else. And then we type check the body, and if it has some type tau prime, then we assign the type tau vector to tau prime. Okay? So we've rigged the type system to make sure that we have the invariant that we really care about, because this is a compiler IR. It's the target of closure conversion. So we want to make sure that we want to make sure that type checking gives us the one property we really, really care about after we've compiled, after we've done closure conversion, which is, it should automatically be able to tell us, yes, you did closure conversion right, and now all of your lambdas do not contain any free variables. Okay? All right. So what we were doing is we had put down a type translation for closure conversion, and then we were about to start translating terms. So let's just do that again. So what we're going to do for the type translation is for every type sigma in the source language, we are going to translate it, and that means we have two cases. The int translation doesn't really do anything, so it just converts int to int, a source int type to a target int type. And then we have the interesting one, which is sigma 1 to sigma 2 functions. Function types get translated as, refresher from yesterday. How did we produce closures? So a closure is going to be a pair of code and an environment, and we use existential types to abstract over the environment, right? So we're going to say there exists an environment type alpha n such that we have a function that takes what? Right, so we have to take first the environment, and then we have to take the translation of sigma 1, which is the argument to the function, and we produce the translation of the result of the function. That's what our code part does. And then we pair it up with the actual environment, which will be represented as a tuple itself. But we don't have to say that it's a tuple. There we go. Okay, so that's our type translation. All right, so the language is up there. Every single term that's written in black needs to be translated into something red, all right, according to this discipline. So, and where I left off yesterday is I said, we're going to do this by induction on typing derivations, okay? We're going to define our compiler or our translation by induction on typing derivations. So what that means is that we give ourselves this sort of judgment form. We say that so what we're doing is we're translating only well-typed terms, right? That's why we're doing induction on typing derivations. So any source term E that has type sigma has to be translated, okay? Now, I got a question right after class about what's in gamma, right? So notice that I'm not translating a closed program. This is very important. I'm translating a source program that might have free variables. So one potential program that I might want to translate might look like this. Is that okay? Is there anything wrong with that? Why am I doing that? Yes? Yes, essentially. So I'm treating these variables as, so yesterday I talked a lot about linking, right? When I say linking, I don't know, most people will think about the low-level notion of the linker and what it does to put things together, right, in like really low-level code. But here, I've been talking yesterday about linking from a very high-level perspective, and I want to sort of say, make it explicit that my mental model here is that when you have a high-level language program and it has some free variables in it, those free variables are the little spots, these little holes where you can come in and plug in, link in other code. Okay? So I want you to work with that mental model. In other words, when I say that I want to be able to compile open programs that might have free variables, what I'm saying is these are willing to accept other code that might be linked in from the context. All right? It's a very important point. It's going to keep coming up. All right. So these are the little spots where my context can provide inputs, right? Link in inputs. So how that might happen is, well, I guess at some point this gets translated to the target. So let's see. I suppose maybe something like this happens, right? And then my model is that my context can provide substitutions for this x and y. And just at an abstract level again, we can say the context does something like this. I want you to see this as I have a component, x plus y, that I have linked into or plugged into a target level context. And the target level context is providing my free variables with inputs, and now we have a whole program. Okay? All right. Okay, so let's come back to our translation. So we have these open terms that we're trying to translate. We're going to do closure conversion. We're going to produce a target term, which I'm going to write in red. And then what we want is we want for this to be type preserving. So this is our judgment form. This is how we're going to translate it. And then we are going to want to prove that our translation is such that I can type check E, and it will have type translation of sigma in the environment where delta is empty, right? Because closure converted code, it didn't have free type variables before. It's not going to have free type variables now. That should be red. And gamma plus. Right? And we defined gamma plus yesterday. Good? Do you want me to put down gamma plus again? It just basically walks over all of the variables and translates them. Okay. You guys are awfully quiet this morning. Is it because it's 9 a.m.? Okay. All right, let's put down gamma plus. So empty environment translates to empty environment, and there, and sigma. Okay. All right. Now, okay, let's work on some easy cases. Let's translate variables. So if I have an x of type sigma, I want to translate it. I'm going to write this as if I have the source language's typing rule right here, but then I'm going to put the squiggly thing in translate. Okay? So if I have the source language's typing rule right here, what do I know? Right? Okay. So what do I translate it to? Help me out. What? Sorry? I'm just going to write red X. I'm going to take my black X's from the source language and turn them into red X's in the target language. All right. How do we translate numbers? Yes? Come on, it's dead easy. Thank you. I'm just trying to get you to talk since it is 9 a.m. Okay. All right. Now, how do we translate? We'll do lambdas in a second. Let's do if then else, the if zero instruction. Okay. So under gamma we have if zero, e, then do e1, else e2. Right. So the normal typing rule says e better have type int because we're testing if it's 0, and then the e1 and e2, which I'll just write as ei, better have some type tau, the same type. Right? So E1 better have type tau and E2 better have type tau. Now, what's the type of this? No, not tau. I'm writing sigmas for the source. Sigma. Okay. So how do we compile this? That's great. I mean, I am trying to do that. You're just pointing out that I didn't leave enough space. Partly I was trying to point out that, the transformation judgment kind of pulls the normal typing rules in, right? Okay, so how are we doing this? We're saying, I want to compile if then else. In the premises, since we're doing this by induction on typing derivations, it means that we're just doing induction on we're taking a term of type E that has type sigma under gamma. Ignore this for a second, right? Those are the objects we're working with. That's what we're starting out with, right? And then basically we're doing an induction over this typing derivation for E, for the source E, okay? All right, so what can I do? Well, suppose that this translates to E. Suppose that these E1 and E2 translate to EIs. Then, what do I produce here? If 0. It's structural, right? Just take the pieces, put them together, just make everything red now. Okay. All right. Okay, so what's next? Lambda, the interesting case, and application. Those are the two interesting cases. Everything I've shown you so far was really just a warm-up and is very boring. Okay, so how do we deal with lambda? I'm going to erase the if that's all right. And maybe I'll even erase here. Yes?
What happens to the types?
Good question. Okay, so you're asking why am I not putting types here on the red side? Okay, so notice what I'm doing is right now I'm defining a compiler, right? Essentially, that's what my little squiggly thing is. My compiler is going to work not by induction on the structure of this expression E. It's going to do a bit more than that. It's effectively working by induction on the structure of the typing derivation of E. All right, so this is my compiler and this is the code I want to produce. The reason I'm not putting any types here for the red E is because after I'm done compiling, I want to prove that red E in fact type checks. That will be part of my type preservation proof. It is not part of my compiler. Okay? All my compiler will do in terms of preserving types is if my lambdas have certain type annotations, the compiler needs to put corresponding type annotations inside the red code that it produces. Okay? And that's enough. Just like having annotations on lambda is enough to type check our simply typed lambda calculus, right? Similarly, having the annotations on the lambdas in the target will be enough to type check the target code. But I'm not actually producing any typing derivations on this side. I am simply producing expressions, and afterwards my type preservation proof will prove that what I have produced, whenever the source program E had type sigma under source environment gamma, we will prove that the compiler produced or closure converted program has the type sigma plus, the translation, under the translated gamma environment. That's what our theorem will prove. Yes?
But I guess why not do it all in one segment and produce these when output you express it the time?
No, it's not that. It's just that I'm asking you to imagine that this little squiggly thing is not a typing derivative. I mean, it's not, it's a compiler. What do compilers produce? They produce compiled code, right? So I just want to produce compiled code. I don't want to produce. So the alternative would be, let's see what we're saying, right? So we're saying the alternative is produce an entire derivation here. That's not, I mean, I see why you're saying that because there's so little gap between, you know, producing the E and then later showing that it actually has the translation type versus just writing it there. And you know, that's the truth in some sense. When we write these type-directed compilations, we are so influenced by what we are supposed to produce that it shows us how to do things right. Okay? But technically, this is a very, very important point. Your compiler is producing red code terms. It is not producing entire typing derivations. Okay? That would be very large. But anyway, yeah?
Okay, so to type check our target's code,
Mm-hmm.
so we do the translated environment. So I have to say that we should focus that?
We will see how that happens when we do the Lambda case. The environment will be in a closure, right? So that's exactly where that will show up. And we'll have to make sure that the Lambda translation actually type checks. Okay? So all I wanted to say here is that we are not doing, you know, derivations here. Not producing that. This stuff, you can think of it as it's sitting in your mind, and you are required to prove it afterwards. It's not what the compiler is actually generating. The compiler is only generating this term right here. It's producing code. Okay? All right. So, let's work on Lambda and application. So, I want to translate a source Lambda. So under gamma, I have a Lambda x colon sigma dot e. It has type sigma arrow sigma prime. And under the assumption that x has type sigma, we type check the body e, and it better have type sigma prime. And now I'm going to turn that into compilation. So we can say that we can go and compile the sub-expression E, right, to get a red E. And now we have to figure out what we want to produce over here. Right? That's our task. Now, as I said a second ago, we're really influenced by the type of the things we are supposed to produce. So whatever we're supposed to produce here, what type does it have to have? Translation of the sigma arrow sigma prime, right? Okay, so sigma arrow sigma prime plus, we have to produce something which is an existential with a pair inside, right? So what do I write down if I want to produce an existential? Pack. Okay, so we are going to produce a pack. The pack is going to have, top level, two things in it. First, we have to specify what the tau is, and then we have to specify what value we're putting in the pack, or what term we're putting in the pack, right? Okay, so let's see. We want a type over here that corresponds to the actual concrete type of the environment, because we're trying to say what will alpha end eventually be, right? Or what it actually is inside the package. All right, so I'm just going to say that it needs to be some kind of tau end. And I don't know what tau end is yet, but we'll calculate it above the line in a second. Or maybe we should do it right now. How do we figure out what the type of the environment is that we're going to produce? What does the environment need to contain? All the free variables of what? All the free variables of E? Minus x, right. So technically all of the free variables of the lambda, right? So let's write that down. We want, let's say y1 through some ym are the free variables of our lambda term. Those are the free variables. We have m of them, let's say. Now, we're still not there yet. How do we figure out the type of tau n? We want to find out what the types of these variables are, right? What are the types of these variables? They better be in gamma. So we can say, assuming that these yi's have type sigma i's under gamma for I in 1 through m. Okay? All right. So we have our free variables. We know their types. So the types of all of the y1 through ym are sigma 1 through sigma m. Okay, now what is tau n? Those types, right? Is it those types? Construct tau n from. You have to take the free variables, the types of the free variables. The type of each free variable is sigma I. Let's take the first one. For type of the first free variable is sigma 1. What type do I put in the environment? Sigma I itself? Okay. It's going to be the translation of sigma I, right? Okay? Or rather, yeah. It's very hard to juggle colors up here. Okay, so we want sigma 1 through sigma m, but we actually need to put in the type environment the translations of the source types, not the original source types themselves, right? Because all of these variables, the black variables, y's, are going to get turned into red variables. And correspondingly, there's a type translation that's happening so that we can properly transform anything that used to be a function into a closure type now, into an existential package. Okay? All right, so that's the type of our environment. That's what we're putting there. Now, the next thing that we have to figure out is what is the function that we're putting here. So there's going to be a pair of some v for the function part, for the lambda part, which we'll figure out in 1 second. And then we're going to pair that up with the environment. And we already know what the environment is. It's going to be the red versions of these variables. Okay? As the appropriate exists alpha, whatever, which is the translation. All right, so what do we not know? We don't know what vf is yet. What did we actually convert the function to, the lambda term? Is everyone with me so far? If not, please ask. Good? Okay, so we are producing a package. We have to specify what the type of the environment is. In order to figure that out, we have to figure out what the free variables are. So we figured out what the free variables of the lambda are. We figured out what their types are. We translated their types and created this type environment type, which is a tuple of all the type translations of the free variables. Now, we are going to produce some code. It's going to be a function, that's why I'm writing as a v function. And it is going to be a lambda that takes an environment as its first input and its argument as the second input, right? Okay, so let's try and write down that lambda. It's going to be something like lambda z. The environment type is going to be tau n, right? If you remember the examples from yesterday. And then it's going to take its argument as input. So what was the argument here? Well, it was this x colon sigma. So now this is going to take a red x colon translation of sigma. Right? Good? And now we have to produce the body. What do we have to do to produce the body? E, the red E that's sitting right here, that should help us produce the body of the lambda, right? Because that's the translation of this one. But where this red E, sorry, this black E had a bunch of black Y's in it, free variables, right? When we did this sub-expression translation, when we translated it to a red E, what did we do? We took all those variables and just turned them into red E's. So what has happened in this sub-translation is that all of the black variables, which are Y's, the free variables, have gotten turned into red Y's. So we can't just put E over here, right? Because then they would be free. So what do we do about those y's? We need to replace them with something. What are we replacing them with? With the projections extracted from this particular environment. Exactly. So what we're going to do is we're going to take our E and basically substitute in the projections. I'll just write it as 1 through m, project out of z, and replace the y1 through ym. And that is the lambda that we want to produce. Okay? All right.
I have a quick question.
Yes.
Could you say again why we're doing the, so I think I understand the closure conversion and what we're trying to do there.
Uh-huh.
And how does the existential type help, or why is it required again?
The existential type is required so yesterday we saw this example. I gave you two int arrow int functions. One of them had two free variables and the other one had no free variables. And I said that if we don't use existential types, assuming we don't use existential types, we ended up translating those two int arrow int functions. Both of them had the same type. But when we translated them, we ended up producing one in which the tau n portion was, a tuple of all of its free variables, and in the other one, which had no free variables, it was an empty tuple. And so basically, that translation suddenly takes two things which have to have the same type in the source and gives them two different types. We can't do that. That's not uniform in some sense, right? So what has happened, like what we saw through that translation, through working through that example, is that this translation is revealing, after the transformation, we're going to be able to tell what the free term variable, how many free term variables any lambda has, and be able to distinguish between them on that basis, which seems silly, right? You can't uniformly deal with those lambdas anymore, right? I have some target level code I want to link with. Conceptually, it's code that wants an int arrow int function. Why does it have to know how many free variables that this particular int arrow int function has in it? So we're trying to hide that using existentials. Okay? Yes?
Is there any instance of some kind of compilation where you do not want to translate the name of file only into the name of file in the other language?
So I'm just kind of making this, simple, but I don't know, don't take that part too literally. You can, that's an engineering thing when you actually do the compiler. I don't know. Okay. Maybe the answer is it depends on your particular compiler path and on the particular intermediate language that you're translating into. Right? When we translate, the best example actually is assembly. When we translate into assembly, when we do code generation, assembly doesn't have any variables anymore, right? Where do the variables go? At some point in the compiler, during code generation, we're going to take an IR, an intermediate language, intermediate representation, that deals with free variables and turn it into something, assembly, which only knows how to deal with registers and maybe passing arguments on the stack. So there we'll be turning variables into registers or stack locations, essentially. Okay? All right. Okay, so that's Lambda. It's big. It's hairy. Now, the last interesting case is application. And application is interesting because this transformation does a transformation on functions, so you have to appropriately transform application as well, right? Something interesting is going to happen there. Now, where should I write it is the question. Let's try. Okay, so let's do application. I have E1 applied to E2. Where my E1 has type, let's say, okay, so application. E1 applied to E2. E1 has type sigma 2 to sigma. where this E2 has the appropriate argument type sigma 2, and we get back a result of type sigma. Okay, so when we compile E1 here and compile E2 here, we get corresponding target code. Right? Now we have to take that and somehow assemble it to produce the appropriate code that does application over here. Right? Okay, so what do you think is the first thing you should do? Sorry? Unpack. Why are we unpacking? What's the first question to ask even? Exactly. So when we write down the red expression that we're going to produce over here, we need to use E1 and E2. What is the type of this red E1? It is the translation of a function type. So this red E1 has an existential type that looks like this. That means that inside that existential type, or inside that existential package, effectively, is where we are going to find the function that we want to apply to this argument. So we have to extract it first, right? So we are going to unpack alpha x, our E1, and then what do we do in the body of the unpack? So what does unpack do? Let's think about it. We're unpacking this thing, which has this existential type. So our alpha is going to get bound to the tau for the environment, and is going to get bound to the tau for the environment, and then our x over there is going to get bound to a pair. Actually, let's write it as P so we can remind ourselves that it is a pair. It is a pair of code and environment, right? Okay, so so since it's a pair, I'm going to have to project out of it to get my function. So if I do a pi1 projection, I get the code part. If I do a pi2 projection, I get the environment, right? And then notice that the way that I will have to use my function is to provide it with exactly that environment first, and then with its argument. Okay, so let's do that. I'm going to have to go into this space here. Okay, so we are going to take our pair. We are going to project out the first thing. This gives us pi1 of p, gives us the function. What does the function want? It wants two inputs. So we are going to apply it to the first input, which we get by projecting out of the pair. That is the environment. And the second input. Where's my second input? Where's my actual argument of type sigma 2 plus? Sorry, sigma 1 plus. Right here. Sorry, sigma 2 plus in this case. Right. So that is just going to be E2. Good? Okay. So any questions about that? Is it easy or difficult to see that type checks? We constructed it in a way using the type invariance in our head to properly put pieces together. Yes?
Can you use the alpha, or do you have to project the second component of C?
Good question. Use the alpha. What do you mean by use the alpha?
Well, so when you unpack it, when you bind that alpha, is that also alpha M, or is that something different?
Okay, so the thing that I'm binding to the alpha is the tau n that's sitting inside the closure after I'm done running E1, right? Okay, so you're saying, do I need that tau n anywhere? So let's see. Basically what we're trying to do, the answer is no, not really. The place where you need it, effectively, is when you are type checking the body of this. So actually, let's do this. Let's do this case, because it's the interesting case. I just claimed that, isn't it easy to see that this type checks? But I just realized that it's not that easy to see that it type checks. So let's make sure that it does. Basically, what we want to do is, here's this unpack that we just produced, and I claim that it is type, the translation is type preserving, which means that this unpack will have what type? Sigma plus, the translation of this, right? So we better be able to show it. Let's construct a typing derivation and actually show it, because the answer to your question lies in that. Okay, so You're going to have to remember the unpack typing rule. So here we have unpack P E1 in pi 1P. We wish to show that this has type sigma plus, but we don't know that yet, right? And we are doing all of this under an environment that is the translation of gamma. And our delta environment is empty. Let's build a typing derivation. How do we type check unpacks? First we say, oh, E1 better be of the proper existential type. Okay? So, what do we know about the type of E1 by the induction hypothesis, right? What I'm doing now is basically one case of the type preservation proof. The type preservation proof is going to work by induction on the typing derivation of this. Let's write down our theorem. I should say if this and this thing translates and then this E has type. That is what we're trying to prove. Okay? So what we're doing induction on is this derivation, effectively, which sort of amounts to doing induction on this, because they're really the same thing in some sense, in terms of structure. Okay, so here's our case. This is the application case. We know that this thing type checks, so we know that these do. By the induction hypothesis, therefore, we know that the red E1 and E2 have the appropriate translation types. That's the fact that we're going to use. So what can we say right here about the type of this E1? The translation of sigma 2 to sigma. So it's going to be there exists an alpha n such that we have alpha n paired with sigma 2 plus to sigma plus, right? And then alpha n. That's the type of my E1. What's the type of my E2? Yeah, E2, we can read it off right here. E2 will have the type that's a translation of this. So it will have type sigma 2 plus. Okay, now remember your unpack typing rule. So actually I shouldn't be type checking just E2. I should be type checking this. This is the body of the unpack, right? We have to show that this thing has the appropriate type sigma prime. Sorry about that. We want to show that P E2 has the type sigma plus. Did I write down the correct thing just now? Is that how I'm type checking the body of my unpack? This is the body of my unpack. Are my environments correct? What did I miss? The translation? No, think about the unpack typing rule, right? Unpack says unpack E1 in E2. The body, this thing, the body of the unpack, can have alpha and P free in it. So I have to put alpha and P into the environment right here, right? That's what I did not do. Okay, so we put alpha there. We already have our gamma plus, but we have to extend it with a type annotation for P. What is the type annotation for P? It's the pair of some tau n, sorry, it's the pair of this, right? Okay. That's the function part. And then we have, so of that, I think I've put enough information on the board now for you to confirm that this is in fact going to type check. Yes?
If sigma 2 is a value, you want to change the translations until you have until the lambda becomes lambda, right? So
I'm sorry, hold on one second. You said sigma 2 is a value, but sigma 2 is a type. You meant E2?
E2 is a value.
If E2 is a value,
Then you don't have a translation, right? Because you aren't showing the translation until you have lambda in the 19.
but this is the typing derivation, right?
Yeah.
The red E2 will get run down to a value, to an actual package, when we run the program that we have generated. Yeah, exactly. So right now the type is telling us that when we run that red E2, its canonical form will be a pack. But we don't need to know what's in the pack right now. The type is telling us enough information about the things that we will get out once we have run it down to a package. Okay? Okay, so does that answer your question as well?
Yeah.
Okay, great. All right. Okay, so that's type closure conversion. Now, what I'd like to do next is basically show you how we use a logical relation to do compiler correctness for this particular transformation. Starting to feel like maybe this material is too heavy for a 9 a.m. lecture. You guys want to? Yeah. If it gets too dense, please stop me. Ask questions. All right. So let's see, what do we want to do? So you have not seen binary logical relations. What I'm basically about to try to construct is a logical relation that relates source expressions to target expressions, black language expressions to red language expressions. And what I want this logical relation, the relation I write down, I will only say that these black expressions are related to red expressions when they are equivalent. And I get to decide what I mean by equivalent. All right? Okay, that's what this logical relation is going to do. It's going to be a specification of equivalence between the source language expressions and the target language expressions. Okay, now, before I dive in, I'm thinking since you haven't seen a binary logical relation, maybe I should show you a binary logical relation for a single language instead of putting two different languages in it. Is that good? Is that welcome? Okay, all right, let's do it. Let's see. Ha! Nice. I'm sorry, I need the space. Okay, so we're going to take simply type lambda calculus, exactly the source language that's on the board, and I'm going to show you how, just the basic technique of logical relations and how we prove equivalence. So, simply type lambda calculus, the language up there, the source. What I'm about to set up will be something that I can use to do proofs of equivalence of programs in this language. Okay? In particular, we can prove contextual equivalence. How many of you know what contextual equivalence is? Has that been covered? Yes? Okay, so you're comfortable with contextual equivalence. All right, good. Okay, so basically, let's see. We'll start simple. We have values in the language, we have expressions in the language. All right? I'm going to start out by defining a value relation that tells me when closed values in the language are related. And I'm going to do this, I'm going to construct this logical relation by induction on the structure of the types. So, basically, the first thing I'm going to do is set up a value relation. It's going to be indexed by the types of the source language. Okay? Right now I'm just showing you the shape of the relation I'm about to create. And what I'm going to put in it is I'm going to say that values v1 and v2 belong to the v relation at the type sigma if, the invariant I'm going to have in mind is that these v1 and v2 are closed values of the type sigma. And then I'm going to write some other conditions which help me check, are they actually equivalent? Okay? So this is the shape of the relation that we're going to set up. So I said we're going to do it by induction on types. That means we have two cases. We have to say when ints are related, and we have to say when sigma 1 or sigma 2 things are related. All right? So help me out. So this is just the shape. I'm just telling you what we are after. Okay, basically the important part here is construct a relation put two values in it, make sure they're of the right type, okay? Otherwise, they're not going to be equivalent. And then go from there. Okay, so, int. When are two values related at the type int? First of all, what values should I put in here? What are the canonical, what values have type int? Numbers. Okay, so I could put an n1 and an n2. And they're obviously going to have type int. I won't even write this part down. I'm just building it with that invariant in mind. And when I'm constructing a relation that should capture contextual equivalence. So when are two numbers, n1 and n2, two integers, equivalent? When they're equal. Okay? All right. Next. Function. When are two functions related? So what shape of values should I put in here? So I need to put in a v1 and a v2, and they both better be values in our source language of function type. So they have to be two lambdas. All right. Lambda x sigma e1, and they have to be two lambdas of type sigma 1 to sigma 2. Let me make this a sigma 1. Right? Or let's make it sigma to sigma prime, otherwise I'm confused with the... Okay. So this needs to accept a sigma, so I've annotated it as such. And then I have another lambda, which also takes a sigma, but it's different. It has a body that we're calling E2. So when are these two lambdas related? How do I check that? How do I specify that? I'm assuming that they're both sigma to sigma prime, have that type, and they're closed. How do I check when two functions are related? Sorry? When you? Louder?
If you put it in some evaluation context, the result is equal.
Okay, so what he said was when you put them in some evaluation context, we want them to be equal, right? That evaluation context, but basically that's exactly the right intuition, because what we're trying to do is set up something that gives us contextual equivalence, right? So what you said is like pretty much the definition of what we want. We want it to be the case that when we take these two values, these two lambdas, and we stick them into any context, we get the same answers at the end. But I don't want to say it for all possible general contexts or even for all possible evaluation contexts right here. Instead, let's think about what evaluation contexts are actually relevant to functions. What's the only interesting evaluation context for application? Exactly. All right, so here's the slogan. In order to figure out if two functions are related, in order to figure out if any two values are related in a logical relation, the first question you have to ask is, all right, how do I use these values? All right? In the case of functions, this is especially important. In the case of numbers, we can very easily figure out when they're equal, right? They have to be actually identical numbers. But in the case of functions and other types as well, the question you want to ask is, how do I use these values? Right? And that's where we got to from this evaluation context discussion. The way that we use functions, the elimination form for functions, is application. So what we're going to say is that when we use these functions and we apply them to related arguments, we will get related results. Okay? And that sentence that I just said, if you give me related arguments, I will give you related results. Related inputs to related outputs is pretty much the slogan of logical relations. Okay? All right. You saw this with the proof that you guys did with Dan for strong normalization for STLC2. You didn't have two functions there, but you must have set it up in a way so that you said, let's make sure that the input to the function has the property of interest, and then I will guarantee, which is termination, and then I will guarantee that the output has the property of interest. Here, my property of interest has just turned from a unary thing to a binary thing. Okay? So we change to saying, if you give me related inputs, then I will give you related outputs. All right, so we're going to say for all v1, v2 that have the property of interest, that are related values at the input type, sigma, right here, it better be the case that I get related outputs. And I'll write that as, if I take the body and substitute v1 for x in the first one, and then take the second lambda's body and substitute v2 for x in the second one, I better get related expressions. I'm going to start writing E relation now instead of V. Instead of the value relation, this is going to be my expression relation. I'm going to get related expressions at the result type sigma prime. Okay? Everyone with me so far? Okay. All right. Now, of course, I've introduced another unknown on the board. What exactly is this E relation? When are two expressions related? So we're going to define this E relation, which tells us when are two closed expressions related. Okay? All right. So let's do that here. I'm going to assume that the expressions E1 and E2 that I put in this relation are both closed and that they have type sigma. Okay? So the invariant is, you know, kind of like this one, only for expression. I won't actually write it down, but they're well typed and they have the type sigma. Now, I'm giving you two closed programs, right? These are closed expressions. You need to tell me whether or not they're contextually equivalent. What do you need to do to check that? Yes.
But how do you know that the expressions will lead to substitution?
Good question. So let's figure out where we are and make sure our invariants are set up correctly. I claimed that I was going to construct a value relation. I was only going to put closed values in it. Correct? Okay. That means, and then here I put closed values in it. And here I claim that what I'm putting in are closed lambdas, which means that both of these satisfy this property, which means that this is closed and has type sigma to sigma prime, and same for the other. So, answer the question, right? And then we are plugging in the only free variables that are in the body. So we still have closed expressions. But that was a good exercise. This is how we sort of trace through a logical relation and figure out that all our invariants that we're setting up are there, you know, that we've done things right. Okay? All right. So that's why I claim that here I am only trying to relate closed expressions. I didn't let myself get to a point where I had open one. So this is my, let's write it down. My EI have type sigma. Okay, how do I know that E1 and E2 are related, are equivalent? Suppose I give you a program and you want to check, what would you do? Yes? Run them down to values. Yes, you have whole programs. You can run these down to values. So this is a simply typed lambda calculus, so they're actually going to run down to values just fine. So we could set this up by saying that there exists a V1 and a V2 such that E1 runs to V1 and E2 runs to V2, and the V1 and V2 are related. Okay? Or we could do this differently. In non-terminating languages, we wouldn't know that there always exist these V1 and V2s such that these are going to run down to values. In that case, you have to be a little bit more careful, and you have to say that if E1 runs down to a value V1, then there exists a value V2 such that E2 also runs down to a value and the resulting values are related. Okay? So you phrase it as an if one terminates, then the other one does as well. Okay. I think I'll actually go with that one. I'll say for all V1 such that E1, so I'm showing you, I could have been more specific, but I'm not taking advantage of the termination in my language. If I was, then I'd be showing termination as, together with setting up a logical relation for equivalence. Okay, so if E1 runs down to V1, then that implies that there exists a V2 such that E2 runs to V2 in some number of steps. This is just my operational semantics. And the V1 and V2 are related in the value relation at the type sigma. Is that readable? Okay, so we ran them down to values, and then we said, are the values related? Why did I need to go to the V relation to ask if the values are related?
Why were we using it for all V1?
Because I don't know what value my E1 will run down to. So I'm saying for any V1 such that, but evaluation is deterministic in this language. It's called by value. So that's just formally how you would write it. For any V1, I don't know what it is right now, but assuming that E1 runs down to a value, for all values that E1 might run down to, there will exist a value on the other side that E2 will run down to, and the resulting values will be related. Yes, Ron? Could you say that louder? Could I say? Yes. So in a terminating language, I can replace what I just wrote with there exists a V1 and in fact a V2 such that E1 runs down to V1 and E2 down to V2. And V1 and V2 are related. And since I am in a terminating language, I can completely use this definition. But I'm trying to show you the more general one. Okay? Because we move out of terminating languages very quickly if we're doing interesting work. Yes?
The other one is not circular, we're going by induction of that, right?
Ah, you put your finger on it. Right? Oh, we're not doing induction on the terms, we're doing induction on the types. Yes. Okay, so actually let me come back to this in just 1 second. I haven't fully finished this definition. So far, because I'm showing you, so if I was giving you this definition, I would be done. Right? E1 and E2 are related if they both run down to values and we get related values. But I'm not using that one, right? I'm not using this one. Is this one complete? What is it saying? If you had non-termination in your language, is this enough? No, why not? Right, we need to say and for all V2 such that if E2 runs down to a V2, then that implies that there exists a V1 such that E1 runs down to V1 and the V1 and V2 are related. It's a symmetric thing, right? You can't just say they're equivalent. If you only want to do one direction, then that means you're getting an approximation relation, not an equivalence relation. Equivalence means you need both directions. Okay, so I just wanted to make that explicit. Okay, so back to the question of is this logical relation inductively defined? Let's check. My claim is that we are doing induction on the structure of types. Okay, so here I'm trying to define a V relation by induction on types. So when I define when values are related to the type int, I better not be using in the definition, I'm not referring to the V relation again, or the E relation, so I'm good, right? Here, I am trying to say when values are related at the type sigma to sigma prime. Inside the definition, I am using the V relation at a smaller type sigma. Sigma is smaller than sigma arrow sigma prime, and at the smaller type sigma prime. So both types are smaller. The only funny business is, but this is an E relation, not a V relation. So let's go inspect how the E relation uses the V relation. All right? Like, effectively, I'm saying let's inline that E relation over there so we can make sure that we're referring to the V relation properly. All right, so here, if we have sigma here, then we only refer to the same sigma. So that means that that definition is only referring to V of sigma prime. So, in other words, this is absolutely inductively defined. If you add recursive types to your language, it will not be inductively defined. You can't possibly do that, and that's where you need step index logical relations. And if you want to know about that, you can watch my lectures from previous OPLSS years. Okay, so far I have told you when closed values are related and closed terms are related. But I want contextual equivalence. Contextual equivalence says when are two arbitrary open terms related? So, just to remind ourselves what contextual equivalence says, E1 and E2 are contextually equivalent at the type sigma that is defined as for all possible contexts of the language C, where a context is any expression with a single hole in it, assuming that the context has the right type, which means that in the hole we should be able to put some term that type checks under environment gamma and produces something of type sigma, which I'll write as gamma sigma is the type of the hole. So given any context with this kind of hole, and assuming that the context, when I plug it with some well-typed E that has type sigma under gamma, I'm assuming that I will get a closed expression of, let's say, the int type. And I'll write that as, I will get back something that type checks under the empty environment gamma and produces something of type sigma. Okay, so assuming that you give me a context that produces an int at the end of the day, that's how I create my whole program. I'm going to say that C with E1 produces n, the same n, if and only if C with E2 evaluates down to n. I've used the down arrow here, but take that as, small step reduction applied till you get to a value. Is that definition of contextual equivalence surprising, or have you seen it in the last 2 weeks? Oh boy. Have you seen it in the last 2 weeks?
Yeah.
Have you seen a typed version of contextual equivalence in the last 2 weeks? No? Matt is shaking his head. Is this thing mysterious? What I said about my context, I have a certain assumption about what is the type of terms that I can put inside the whole of the context, and what is the type of the things that I get when I plug the context with an expression. Okay, I want the 2 p.m. lectures. Just for my technical days. All right. Okay, so I hope this is clear, but this is contextual equivalence, right? And this is what we're trying to capture. Now notice the contextual equivalence says when are 2 expressions that are open, they have free variables sitting in gamma, so when are 2 open terms related? So far I haven't shown you anything in this logical relation that tells me how to relate open terms. So I claimed that I'm going to use this logical relation to prove contextual equivalence, which means that I have to scale it up now and tell you how the logical relation is going to relate open terms. Okay, so here's how we're going to do that. We're going to take the definitions that we've built up so far. Yes?
Sorry, but can you tell me more about that?
Okay. All right, thank you for asking. All right, so here when I write this, just basics first, when I say E1 and E2 are equivalent under gamma at the type sigma, I am assuming that each one of these E1 and E2 have type sigma under gamma. Okay, that's an important first assumption. So 2 well-typed things of this type are contextually equivalent if, for any possible program context, so imagine that a program is this big circle, this is my context, and it has one hole in it. Okay, so imagine a very large software system, it's sitting there, you have a lot of code here, and you are trying to take one piece of that code, the E1, and replace it with E2, all right? What I'm trying to say is, this is a well-typed program, so you can't just take a hole in the program and put in something that is not well-typed. Because I want to make sure that I put in well-typed pieces into that hole so that overall my entire program remains well-typed. How do I capture that? I have to say something about what is the type of the expressions that this hole can accept. Okay? And what I have in mind is that it can accept any expressions E that type check under an environment gamma, a particular gamma, and produce something of type sigma. And that is what I'm saying here. So what I say, this is a context whose hole is of type gamma sigma, means you can put in E's which have type sigma under gamma. So that's the type of the hole. And when I plug the hole with well-typed expressions of this type, I will get back a complete program, C with E2 in it, which will have the type int under the empty environment gamma. Yes. I picked int because, good question. Why isn't it function, right? Of course you can create programs, entire programs that are closed that produce functions. But the problem is, if I allow myself to put a function type here, then notice I won't be able to say that C with E1 goes down to the same exact value as C with E2. I'll be getting 2 lambdas. And then I'll have to say, oh, when you take these lambdas and put them in some larger context, then you run it down. But the moral here is that it suffices to restrict your contexts to results of ground type, booleans or ints, which you can easily compare syntactically, right? You can compare booleans. You say both have to be true or both have to be false. You can compare numbers. You say they have to be syntactically equal. You cannot get contextual equivalence for functions by saying syntactic equality. That's too restrictive, because lambda x, x plus y is equal to lambda x, y plus x, right? Just to take a very simple example. Those are equivalent but not syntactically equal, and that's what this definition is trying to capture. Okay, so that's why we allow ourselves to restrict the result type to be ground, because you can always put more context on the outside, right? This is for all possible contexts. So if you really want to produce some functions, you can always put more context outside to test them, so to speak. That's why this is sufficient. Does that answer the question? Okay. Cool. All right. So yes. So I'm very cleverly saying that pick contexts which result in ground types in integers, and then I'm saying when you run C with E1, you get back some value. If you run C with E1 and you get back a value, in this case it has to be a number, then that implies, this is an if and only if, right? Then that implies that C with E2 will produce the same value. We could also write it as this produces V1, this produces V2, and V1 and V2 are equivalent, are equal, syntactically equal. Okay? All right. Okay, so let's see. That is contextual equivalence, and now we are going to define our open logical relation. I'm going to give it a very similar looking shape, but I want you to remember that this symbol, which does not have this contextual CTX sitting on top of it, is my logical relation symbol. So I'm going to say E1 is logically related to E2 under the environment gamma at the type sigma if something. Okay? How do I define it? Well, let me write down my assumptions. I'm assuming that E1 has type sigma and E2 has type sigma under gamma. Okay? And then what I want to do is the following. These are open terms. So there are a bunch of free variables that are sitting in this gamma. We need to close them off. Okay? So there are a bunch of x colon sigma prime kinds of assumptions sitting in there. We need to take all of those x's that might appear anywhere in these two terms and plug them with related inputs. And if we can plug them with related inputs, then all we need to do is that we get back related outputs. Okay? And that will be contextual equivalence. Notice how it's sort of reminiscent of what we did here? Only here we were dealing with a single lambda. Now you can think of it as if we're dealing with lambda bodies which have all of their arguments sitting out here. Okay, so let's do it. You have to give me related inputs, but I have a whole bunch of different variables. So I'm going to define this notion of related substitutions for some environment gamma. Okay, and I'll write that as G gamma gives me related substitutions, and basically define that as two substitutions, little gamma 1 and gamma 2. What are little gamma 1 and gamma 2? Gamma is going to be something of the form x1 maps to v1, x2 maps to v2, etc. It's just a series of bindings. It's a substitution. It maps variables that are going to be in this environment to values of the right type. Okay, so gamma 1 and gamma 2 are related substitutions if for all x in the domain of the environment, gamma 1 of x and gamma 2 of x, in other words, these values that we have sitting in each one of the environments, are related values at what type? What's the type of these? Gamma x, exactly. We can look it up in gamma. All I'm doing is for every single one of these x's, please give me two related values, v1 and v2, such that they are related in my v relation. Right? Those are my related inputs for all my free variables. So let's finish this. If you give me two related substitutions that are related according to my related substitution relation, then when I use those substitutions to close off these terms, which I'll write as apply the substitution to the expression, and substitute all the x's with the values that are in the substitution. Now these guys are closed programs. So I just need to say that they are closed expressions that are related at the appropriate type sigma. Okay. So that's a logical relation, and I claim that you can use this to prove contextual equivalence. And now you have to do some proofs. Normally, when you set up a logical relation, you have to prove a property called a fundamental property, which I'm sure you saw when you did strong normalization. Yes? Yes? Here, strong normalization, sorry, here the fundamental property this is the theorem. It's called the fundamental property of the basic lemma that you have to prove for every logical relation. But here there is something interesting. I have to prove that if I have a well-typed term, E of type sigma under gamma, then it is related to itself. Where that relation is my logical relation up there. Now, does someone want to ask me why I want to prove that it's related to itself? Yes, but doesn't it seem kind of boring? I'm wondering if some people think it seems boring to just show that an expression is related to itself. And if it's not boring, why is it not boring? Why did we do all this work? Stare at the definition and tell us what it's hiding. The free variables. The reason it's not boring, even if I make the E1 and the E2 exactly the same E, it is not a boring definition because it says here's some component, here's some program with a bunch of free variables. I'm going to plug those free variables not with identical inputs. In that case, it would be boring. I'm going to plug it with related inputs. And those related inputs can be pretty different from each other syntactically. And that's the whole challenge, right? Dealing with that syntactic difference between two programs that you are trying to prove are equivalent but not syntactically identical. Okay, all right. So I was not really supposed to do this entire digression on simply typed lambda calculus and binary relations for that. But since it wasn't covered by Dan or Bob, I thought, you really ought to see this. So let's try to now be very clever in the next 10 minutes and scale this logical relation to do compiler correctness. And here's what we're going to do. We're going to do some editing. We have a logical relation on the board. It relates two terms off the same language, off the source language. All we're going to do is change the term on the right-hand side. Okay? So we want to prove compiler correctness, which means that we want to be able to take all right, so we're going to follow the same structure. I'm still going to tell you when closed values are related at every single type, only now my relation is only going to be indexed by the source side of things. And I say that this is the right thing to do because it is those source programs where we started, right? Those are the things that we're trying to relate to some target programs. So I want you to think of this as we're indexing by a source type. So the value that we have over here, this black value that we have over here, V, is going to be of type sigma, this type right here. But I'm going to put a red value on the other side, okay? And I'm going to insist that that has a translation type. Okay? Instead of same two black values of the same black type sigma, we're going to have on one side a red value of the translation type. We're just setting up a relation, right? And it's going to go across languages now. Okay, so let's repeat our exercise. I said we could be clever. Okay, when are two ints related in the source and target? When they are the same exact number, just in different colors. Okay, function types are interesting. Okay, so what do we need to put here? Well, here we have a lambda, right? Get rid of my 1. So I have a lambda xe in my source. On the other side, I can't put a black value anymore. I need to put a red value, and it needs to be of what type? An existential type, which is the translation of that function type, right? Okay, so so I need something that is I need a red value, closed value, that has the translation of this type. So what is this canonical form? It's a pack. Okay. All right. Pack of what? How do I know what the environment type is? The question to ask ourselves right now is this one. Look at that type translation up there. What is the most information you can extract about the shape of this red pack that I need from just looking at that type translation up there? Give me nothing more and nothing less. What do you have? It's going to be a pack. So I'm asking you to look at the translation of the sigma 1 over sigma 2. It's going to be a pack. It's going to have some tau n in it, right? Okay, let me throw a little thing at you. We could do this kind of reasoning. This is a closed function. Yeah? Closed function? No free variables? Oh, yeah, so it makes perfect sense for it to be the empty environment, right? Okay, let's just make it the empty environment and proceed. Let's see what happens. Okay, so my pack is going to have empty type for the environment. This is my environment type. And then the other thing I know it has is a pair. And the first thing in the pair is a function. Okay, so what should I write down? What do I know about the canonical form of that thing? If I know it's a function, remember this has to be a value. So I need a pair of values here, correct? Okay, pair of values, we're good with that. Next thing we know, do we know what the shape of the second thing in the pair is? We don't actually know it's a tuple. All we know is it's an alpha n. So I'm going to say that what I need to put over here is just going to be a function, and okay, how do I know it's a function? It's a value and it has to be a function type. So that means that it has to be a lambda, right? There's just no other thing that I can put over there. Empty environment type, because I'm just taking what has to be here because that's my constraint, right? Okay, and then it takes a red x, where we had a black x over there, of translation type. Yeah? Okay. And then, well, it's a function. Do we know anything about the body of the function? No, we know it better have result type sigma 2 plus, but, or in this case sigma prime plus, but we haven't gotten anywhere else yet. So I'll just put an e. We don't know anything more. Okay, so that's my function. And then I have an environment. I'll just write it as Vn, because I don't know what it is. Oh, is that right? I do know what it is, because I put tau and there is empty, right? So, there. Are we happy with this? Yes? Okay, we constructed it from that. All right, now, let's close some parens and try to say, when are these two things related? Trust me, we're going to do exactly the same exercise we did before. Two functions are related when you give me related inputs and I get related outputs. This time we just have a red pack over there that we're going to need to sort of pull apart, unpack. Okay, but do exactly the same thing, related inputs to related outputs. So, how do we say that? By the way, I have thrown you a little bit of a, let me fix this before I go on. Because I could come back to it too, but I'll do it right now. I tricked you guys. I asked you what is the type tau n, right here. And then I led you astray, quite intentionally, by saying, oh, this is closed. So we could just put a closed type here, right? And while that answer answer is perfectly correct, you don't need to do that. We are dealing with some package of existential type. You can put the power of existential types is such that nobody outside the package needs to know what this tau n is, which means that you don't need to do this kind of analysis. Oh, what am I relating it to, and will it always be closed? You don't need to do that at all. All you need to do is say there is some tau n, and it just needs to be the same one in all of the relevant places. And the power of existential types is such that as long as that Vn ends up having that type tau n, you're going to be absolutely fine. Okay? Yes, that we will. Okay. So, let's see. Now, so we want to say when are these things related? Well, related inputs. So, for all, we need a related input for the black X, we need a related input for the red X. Okay? So, for all black and red inputs that are related at the argument type sigma, which means this will have type sigma, this will have type sigma plus. Now we're going to take our inputs, plug them into the things, and run things. Okay. So that means running on this side means take the E and substitute the black V for the black X. What does running on that side mean? What do we have to run? This guy, right? We want to run the body of the function, just like we're running the body of the function with the input plugged in. There we want to run that red E with our red input plugged in. It's just that there's sort of nasty stuff around it that we have to deal with. Okay, so what do we do? Basically, this red E has a red X that's free that we have to plug. Clearly, we want to plug that with our red V. But it also has this Z that we need to plug. What do I plug that with? Right. The Vn is precisely the thing that we get to substitute there. So, substitute Vn for Z in E and substitute our red input V for the red X, and then show that these two things are related at the results type sigma prime. And again, this means that this guy will have type sigma prime when we run it, and this guy will have type translation of sigma prime. Good? Okay. Let's edit this. Is it going to be easy or hard? When are two expressions related? One is the source and one is the target. This one has type, black E has type sigma. Our red E has type sigma plus. Maintaining the same invariant that we've had throughout. And then all we need to do is say for all black V's such that the source term evaluates to that, there exists a red V, you get the idea, right? Such that the red expression runs to a red value, and these are related. And vice versa, right? I know it's not nice to edit on the board. I know you guys have trouble taking notes, but in the interest of time. And I don't think that the editing was too conceptually difficult, right? Okay, so we have just changed our entire single language logical relation into a cross-language logical relation that I claim we can use to prove closure conversion is correct. Okay? Why are we getting closure conversion is correct? Oh wait, I didn't edit that part. But it's an easy enough edit. We're going to say this is going to be our top level specification of when a source component and a target component are to be considered equivalent. And what we have in mind is that the source component has type sigma under gamma, and the target component, mind you, we've already proved type preservation, right? Now we're doing closure conversion is correct after we've proved type preservation. So we're going to say that the red E, when we try to type check it under the translated environment, okay? So I'm relating something of the original source type with something of the translated type. These two things are equivalent if I plug in related substitutions at the type gamma, and I get back related answers. Part of the point of doing this in this style was to show you how conceptually simple it is to take the, once you understand the idea of how logical relations are set up, you can set up single language ones or cross language ones or whatever. The ideas remain the same, the structure remains the same. Okay? And using words like, I want related things to go to related things, help you figure out where you are. And beyond that, all you need is to remember what are the types of the terms that I'm putting inside. They're invariants. And keep them consistent. And it's very easy to set up. So, at the end of the day, now here's my compiler correctness theorem. Remember before we were proving the fundamental property. If a source E is well typed, then it's related to itself. The fundamental property now is actually the compiler correctness theorem. Notice we don't have a definition of contextual equivalence anymore. So I can't say that this logical relation definition that I wrote down corresponds to or is equivalent to the normal definition of contextual equivalence. I want you to really pay attention to what I'm saying right now, because it's going to be very important for compiler correctness. We don't have a notion of contextual equivalence that we can use because we are working with two different languages. Contextual equivalence says if you give me a closing whole program context, but in this case it would have to be black, and you would have to put something black in it on one side and something red in it on the other side. That makes no sense. Right? Yes?
So if we don't need to have contextual equivalence, then why do we care about extending the logical relationship to open things?
Because I want a correct compilation theorem for open programs, because I claim this is compositional compiler correctness, I'm compiling components. And earlier in the lecture I said, any program that has free variables is what I'm considering a component because it can have its free variables plugged in or linked in with other inputs. Okay, so the theorem that we are now proving is the fundamental property, but much more usefully, it is now what we should call compiler correctness, compositional compiler correctness, because we're doing it for open terms. And it basically says that if you have a well-typed source program and you translate it using your closure conversion translation, then we already know the red E is well typed, so that's not what I'm after, right? What I'm after is the source E is logically related and therefore equivalent, because I specified this carefully, to the code that I produced. And here I will put the type sigma, but the assumption is that this has type sigma and this has type translation of sigma. Okay. This fundamental property is, of course, proved by induction on the structure of this typing derivation, exactly like you did the proof for strong normalization. The structure is exactly the same. But what I'm trying to sort of say is, again and again, is now this is a cross-language relation, so you're getting the fundamental property is giving you a compiler correctness result. All right, here's what I'm going to do tomorrow. We're going to come back to this method of proving compilers correct using this idea of cross-language relations, right? And we're going to talk about what some of its, we're going to talk about some of the history, and we're going to talk about some of the drawbacks of this approach. Okay? There are drawbacks. All right.